Okay. Hi, everyone. Really excited to be here. This is my third time at the conference, and I'm always amazed by the spirit over here. If you go on to the next slide, please. Thank you. So I'm Jaya Kawale. I'm the VP of Engineering, leading all the machine learning efforts at Tubi. And today I'm very excited to talk to you about machine learning at Tubi and how machine learning can help power free movies, TV, news, and even sports for everyone. So let's get started. To the next slide. So Tubi, if you have not heard of it, do check it out because it's a free service. It's an advertiser-based video-on-demand service, which means that you can watch any content that is available online for free, except that you'll have to bear with ads. We claim that we have the largest catalog of free movie, TV, and now we also have news and sports. We have about 51 million monthly active users, and the number has only been growing. And Tubi is available across several countries, including US, Canada, Mexico, and even some countries in LATAM. So how can machine learning help in the AVOD space? So there are three main pillars in an AVOD space. So one, the most important pillar, of course, is the user or the audience. The second pillar, again, equally important, is the content pillar. So content is any titles that is available at the service. And the third and the revenue-generating pillar is the ads. So of course, we cannot survive without any of these three pillars. And machine learning can help each of these pillars in different ways. So for example, for the user or the audience pillar, machine learning can help surface titles that are relevant to the users and that the users will click on and watch. So as a result of this, bigger audience means more ads being watched. On the ad tech side, machine learning can help on the ad tech side by improving the ads experience for the users, and as a result of which, more revenue from ads means the ability to buy more and better shows. On the content side, machine learning can help understand the content itself. So once we understand what titles resonate well with our audience, we can try to get more of those titles, and more and better shows means we can retain the users much better. And not just that, maybe we can even attract more new viewers. So similarly, balanced and relevant ads means happier viewers, bigger audience means happier content partners, and more content definitely attracts more brands to advertise on the service, and more revenue means happier content partners, providers again. So this is a cycle which is very, very important, and as you can see, machine learning is a very critical component of an AVOD service. So let's move on to to an important pillar, which is the content pillar. Let's talk about how machine learning can help with the content understanding side. So with every piece of content that is available at Tubi, we have a lot of metadata information available from various third-party sources like Grace Notes, IMDb, Rotten Tomatoes, Wikipedia, and a bunch of other sources. So what does this metadata consist of? This metadata could consist of plot synopsis, cast information, genre information, box office information, ratings, even the language of the movie, and not just that, we can also leverage images or the posters that are there for each and every movies, and the video trailers, and even the videos themselves. So content understanding is basically about understanding all this rich metadata that is associated with a content. And understanding of content can help us with several downstream applications. For example, recommendations, of course, the biggest primary application. Content acquisition. How can we bring in titles that resonate well with our audience? Cold starting of titles. How can we cold start titles better so that they can find their audiences quickly? Image ranking, or the ranking of the artwork that we show when you log on to the home page. For each and every title that you see, the image that you see is actually personalized. So what image you see is different from what image I will see. Also, content understanding can help in the content categorization itself. So you can probably group together different categories of content automatically, and that can help you find niche categories of content maybe certain sections of the users might be interested in. So let's look at some of the things that can happen on the content understanding side. And over here, I have clubbed together both NLP and computer vision-based tasks. So there can be some easy tasks. By easy, I mean which have been solved for the past several years or maybe even decades, like keyword search, sentiment classification, to a little bit harder tasks like topic extraction, embedding generation, and to even harder tasks like understanding the natural language itself, understanding the video or the trailers themselves, and as said by the other speakers as well, using both the text and images or video data and using the modern models like CLIP to understand multimodal data. So lots of things that can be done with content understanding. And moving on to the next one. So I want to touch upon some of the lessons that we have learned in the process. And I want to share with you some of the insights that we gained in the process of understanding content. So the first and the very important lesson that we learned is that pre-processing and cleaning up is very critical. Like it may seem intuitive to you, but I want to repeat, pre-processing and cleaning is extremely critical, because otherwise, whatever garbage you input into the model, you'll only get garbage out. So you need to be extremely careful about what goes into the model. The other thing that I want to mention is that you need to be careful, now that you have different kinds of text available, you need to be very careful about what is the downstream problem that you want to solve. And different tasks require different text. For example, if you want to do some kind of a summarization, you should be probably looking at synopsis or plot summary or whatnot, and maybe do some keyword extraction on the basis of that, rather than using reviews. And repeating the same point again, not all text is the same. Very different text. Reviews is very different from subtitles, which is very different from synopsis, and which is very different from cast information. So we cannot treat all of this textual information in a similar manner, and you cannot just throw in all the information into the model and expect magic to come out of it. So depending upon the task, you should see what text is applicable and go from there. So another thing I want to mention is that pre-trained models like BERT, I think a lot of speakers have spoken about BERT. Yes, they are readily available, and they are easily accessible as well. So, but the other thing is that be careful with the choice of the algorithms. And especially if you're using off-the-shelf trained BERT models, just try to understand a little bit about the model themselves. Like, what was the model trained on? What was the task that was meant for this pre-trained BERT model? And the BERT model, which is pre-trained, is for next sentence prediction. So remember that there is no free lunch available in terms of algorithm and representation. So if you want to use the BERT model for your own task, for example, we were doing it for reviews, and we realized that we absolutely need to fine-tune the BERT model. So just be careful about these nuances, and be careful about the choice of the algorithms. Another thing I want to mention is that averaging, which is very, very widely used by like everyone. So just to give you a brief example of what I mean by averaging. So let's say for a title, we have about 100 reviews available. And ultimately, at the end of the day, what you want to do is generate a single embedding for a title. So one simplest thing one can think of is just take all the reviews, get the embeddings out of them, average them, and there you go. You have embedding for a title. But the biggest loss that happens with this averaging is that you lose information. So be very careful when you're doing some kind of averaging. And there may be like more fancier approaches like transformers based on fusion, which may be more applicable rather than using blunt averaging. So be mindful of that. Last but not the least, I want to mention that evaluation is very hard, but is extremely critical. Especially for natural language processing and computer vision based tasks, you will see that there is like lack of labels available, and but this is an extremely, extremely critical task. So assessing the quality of embeddings, and embeddings generally you will see that help power a lot of downstream applications, not just recommendations, but also cold starting, maybe also content acquisitions. So how do you evaluate the quality of the embeddings that you get out of these models is extremely important, because you may change some parameters and you may get another embedding. So should you evaluate your embedding on each and every downstream applications, or should you just evaluate on one or two applications? So here our take is that like we need to create like appropriate surrogate tasks to evaluate the quality of the embeddings. And this is very, very critical as well, because embeddings are the powerhouse for most modern recommender systems. So here we present what we did at Tubi was that we created a platform, which we call as the Spock Platform. The platform helps with data ingestion, pre-processing, and cleaning. And it helps generate a variety of embeddings powering different use cases. The embeddings can be very simple, like doc2vec embeddings, or could be embeddings like BERT embeddings. And very recently, we're also trying knowledge graph kind of embeddings. And we also have a system or a mechanism in place as of now, which can help assess the quality of embeddings via surrogate tasks. So yeah, here's the overall picture of the platform. We take first and third-party data sources, we take all the metadata information, and we generate these huge bunch of embeddings, contextual embeddings, genre embeddings, demo embeddings, actor embeddings, whatnot. And these embeddings can either be used directly in the downstream applications, or they can even be models which can be created using this platform, which can help power different use cases like cold starting, content value assessment, portfolio analysis, and whatnot. And these are some of the use cases that we have recently looked at, and the number is only growing as of now. So let's move on to the next important area where machine learning can help, and which is recommendations. I'm very sure each and every one of you in the room is aware of what recommender system is, so don't need to give you any introduction over there. But I'm very proud to say that the entire Tubi homepage is generated by machine learning. So if you log on to the Tubi homepage, you will see that there are various content organized in various categories. So we have a content ranking algorithm which can help rank the content which is relevant to a user, a container ranking algorithm which helps rank the containers or the rows which are relevant to the users. We also have ranking algorithms for image ranking, for cold starting of titles, for search, for notifications, for autoplay, and even for generation of the containers themselves. So overall, there are 70 plus models that are operating on the Tubi homepage, and that help organize the Tubi homepage. So we rank the content in containers, as you can imagine, based upon the user features, past interaction, and also with the help of the content understanding embeddings that we get out. And the ranking is typically based upon gradient boosted decision trees. and also deep neural networks. And of course, we also have a two-stage ranking process for a lot of these models. The first stage is the retrieval stage, wherein we cut the candidate space to a smaller number, which can then be ranked by the ranking model. The retrieval system that we have at Tubi is also based upon embeddings, and we have a ton of embeddings. These embeddings not just come from the content side, like I spoke about earlier, like BERT, Doc2Vec, knowledge graph, but also are based upon interaction data. Interaction data is extremely, extremely useful as well, and as you all know, like interaction data helps power the recommender system. So models like 2Tower and others are also used for generation of these embeddings. We have distilled models for new users. By distilled model, I mean that smaller models, because for new users, we cannot, of course, have any feedback or interaction data. So we created these distilled models which can help recommend content better to the new users. And of course, we also have exploration strategies for new titles. And very recently, we also have success with new users as well. So you would think that recommendations or personalization is a solved problem. But it's not actually a solved problem because there are lots of challenging nuances that we need to consider when we are building these recommender systems. And the very first or the second generation of machine learning systems that we build ignore these challenges and only focus on the problem of accuracy. However, the problem of recommendations is actually a problem of beyond accuracy at the top. And there are several challenges that arise from various things. For example, offline versus online metrics, feedback loops, changing tastes in catalog, and also algorithmic fairness and biases. Yeah, so it's definitely not a solved problem. It's beyond accuracy at the top problem, just, yeah, lots of challenges ahead. So let's look at the first problem, offline versus online. Typically, when we try to train an offline model, what we try to do is typical offline metrics that are used are some ranking metrics like NDCG, NMRR, precision at K, recall at K, and whatnot. And typically, what we try to do when we are looking at the A/B test online is that we want to increase the user streaming and retention. So as you can see, there is a mismatch already between the offline and the online side of the world. And let's look at the next slide. So where does this mismatch arise from? And this mismatch leads to the classic problem of correlation versus causation. So let's look at offline evaluation a little bit more closely. So the offline evaluation is based upon historical data. The historical data is cheap, fast, and risk-free, and it's correlation-based because like whatever you show, you can only collect data for those things. You cannot collect data beyond that. And there is, as a result of which, there is this beautiful problem of counterfactuality of rewards. That you cannot capture in the offline data what would have happened if I would have shown another recommendation instead of this one. The online evaluation, on the other hand, is considered to be the gold standard way of evaluating things. The typical way of online evaluation is that you create a randomized experiment in which you randomly split your population into two groups, treatment and control. And the treatment group gets your new model, and the control group gets probably the production model. And you wait for days before you compute the reward. So this is definitely a reliable method, but the problem is that it's also very expensive. So there are, apart from these things that I talked about, like offline and online evaluation, there are also other nuances which influence the collection of the data and because of which offline evaluation becomes even more challenging. Recommender dynamics can affect the performance in ways that are not captured by the offline metrics at all. For example, and this is very, very typical. You can have some kind of an impression cap. So let's say if I show you a title again and again, you may not like it. So typically what everyone does is that you have some kind of an impression cap that after I showed you this title 10 times and you did not click on it, I shouldn't show you this title. So there you go. It creates this dynamics which cannot be captured by the offline evaluation. The other thing is that recommendations can help influence the user preferences in ways that are not captured by offline metrics. For example, did you watch this title because I showed it to you? Or would you have watched this title anyways? Sometimes I already know the title that I want to watch on Tubi, so when I log in, I see it. Oh, there you go. I see my title on the very first position. Go ahead and click it. But should the attribution happen to the algorithm? Or anyways, I was going to watch the title. So why should I even attribute the algorithm for recommending it to me? So this is a very, very challenging problem. So there are user dynamics and other confounding factors which can also influence your decision and watch behavior, which cannot be captured by offline metrics. Example, watching a title because maybe my friend told me, okay, this is a good title, you should watch it. So these things, these are like various nuanced dynamics which cannot be captured by the data that we collect, but which actually influence the decision of a user to watch a title, and which needs to somehow be taken into account when we generate these metrics. So here comes the beautiful theory of counterfactual evaluation, and it is a growing area, and I'm just telling you a very, very quick summary of it, but I would definitely encourage everyone to check it out. And the idea behind counterfactual evaluation is that you should be able to estimate the potential outcome of a policy offline using your log data. So you really don't need to go into an online experiment to check how well your policy will perform, but offline itself, you should be able to check how your policy or your algorithm will perform. And there are a couple of ways that people do these counterfactual evaluations. Some of those processes rely upon generating exploration data or like uniform exploration data and then trying to see how you can make a statement on the reward for the policy itself, or there are some approaches based upon inverse propensity scoring. So the idea behind inverse propensity scoring is that you need to importance weight in order to account for the mismatch in the distribution between the log data and the policy or the algorithm that you want to evaluate. And there are several variants around these inverse propensity scoring schemes, like CIPS, SNIPS, etc. And this is a very, very rich area and fast growing area as well. So definitely check it out. Another thing I want to mention is feedback loops in changing user taste and catalog. As I very proudly mentioned to you that there are 70 plus models operating on the Tubi homepage, but you can imagine that these different algorithms and models create a feedback loop which makes the offline data collection even harder to parse. So different algorithms on the homepage influence, first of all, they influence one another. Let's say if the algorithm on the featured or the topmost container is not good enough, maybe people will go to the second container and click titles on that. The underlying data itself influences the algorithms because you're using the underlying data to train the new models that you want to deploy. And recommendations, of course, influence the watch behavior. Sometimes you watch a title because it has been recommended to you. And watch behavior influences the data that you collect. So there is this vicious cycle and feedback loop that you need to get out from. So typically what happens in offline training, you rely upon clicks, watches, and plays, and implicit feedback has inherent biases. The position of the recommendation also influences the data collection. So many a times, I think everybody knows that, the CTR of a title on the leftmost position is higher than the CTR of the title on the rightmost bottom position. So these positions influence the data collection as well, and which influence the next algorithm or policy that you want to deploy. So another thing I want to talk about is changing user taste and catalog. So the users themselves could adapt and change their preferences over time. I may like comedy last month, but this month I may be more interested in horror. Also, the other important thing is that the catalog itself is very dynamic. It's changing because some titles come into the service, some titles leave the service, and of course there is uncertainty around new users and titles. Apart from this, there are also trends which influence the watch behavior. Here is one thing that we have tried at Tubi, and that we have found, and this is like a still a work in progress area, but that we have found like successful in some of the areas at least, is trying out more of exploration and bandits. At the heart of the algorithm, of the bandit algorithm, is this trade-off, whether you should explore unknown choices to gather more information, or whether you should exploit the known preferences. So exploration definitely helps break the feedback loops and helps with the uncertainty around new users and new items. However, it comes with a big caveat. Designing good exploration strategies that work well in practice is still an art. So there are lots of challenges in real-world practical recommender systems that are not captured in many of the bandit papers. For example, there is non-stationarity of the data, non-stationarity of the rewards themselves. The reward distribution keeps changing. It's not a fixed distribution. The large dynamic action spaces that I spoke about. And another challenge with these contextual bandits is that the reward itself is myopic, which means that the reward itself is short-term and you are not focusing on the long-term. But ultimately, what you care about is some kind of a long-term reward, some kind of user retention or user's joy reward, which you cannot capture by a contextual bandit algorithm. And which leads to the road to reinforcement learning kind of algorithms, which again are come with their own set of caveats and nuances, and which we are just beginning to explore as well. Last, I want to talk about the issue of algorithmic fairness and biases. And in the morning, there was a very good introduction to why this algorithmic fairness and bias is important. And that was in the context of job recommendations. But even for us, if you think about it, the ranking function's goal is to just rank the items given a context. It's kind of a learning to rank problem. And, or you can treat it like a slate recommendations problems. You are given a slate and you need to fill the slate with titles. So the key question over here is, are traditional methods that you do to rank the system, learning to rank or slate recommendations, are they fair or not? So there are many aspects which are ignored by these algorithms. So for example, there are many aspects which could relate to correlation versus causation. So gender and race are the two most sensitive variables that we are aware of, can be correlated with factors that shift the distributions. And there could be several reasons for this bias. It could be just skewed examples, it could be tainted examples, it could be limited features, you do not have as much data, the sample size could be very small. So all these things exacerbate the issue of fairness. There are a couple of things that can be tried for fairness or algorithms. So things like pre-processing, in which before you actually give your data into the model, do some kind of some pre-processing to make sure that the distribution of sensitive or protective variables are not biased. Or in processing, in which the model itself takes into account some kind of a fairness objective, so that the model itself can yield to a fairer algorithm, and post-processing techniques in which you apply transformations to help improve the prediction's fairness. Okay, There are lots of challenging problems in content understanding, users, and also in recommendations that I spoke about. The road ahead is very, very exciting, and we need to go deeper into all of these techniques, and we are hiring as well. And finally, I want to acknowledge that all the work is done by my awesome machine learning team at Tubi. Thank you so much.
Thank you. Thank you so much.